All right, yeah, so as you can see, the talk is called A Brief Opinionated History of the API. It's not brief. I gave it in a 1 hour slot at UPSLA. I have been informed that I have at most 40 minutes, so I'm going to talk fast. A while back, some guy asked me, hey, how did APIs develop in the history of programming? Now, it turns out that it was a federal judge who asked me that question. But still, you got to admit, it's a really good question, right? And the federal judge in question is no ordinary federal judge. He happens to have a mathematics degree and know how to program. Anyway, so the rest of the talk, what I'm going to do is I'm going to answer the judge's question in detail and discuss some related questions. How did the API come to be? What makes them successful? Then, in honor of the judge, I'll take a brief legal digression, and then I'll conclude. The talk is heavily front-loaded. The first section takes a lot of time, so don't worry. Don't think it'll take an hour. All right, so first we have to start with a preliminary question. Before we can discuss the API, who invented the subroutine library? Well, it turns out the term first appeared in Goldstein and von Neumann's Planning and Coding of Problems for an Electronic Computing Instrument, which was this wonderful set of documents that von Neumann and Goldstein put together when they were working on what would become the EDSAC. And this book went out to every lab that was building computers in those days, which was post-war. Everybody got it, and it was enormously influential. And it contains the key idea. It says, most programs will make use of common operations, and a library of subroutines would reduce the amount of new code that you have to write, and of course it would reduce the number of errors in your programs because the library of subroutines have already been tested, right? And here it is in, well, black and white. It's not really black, but it used to be black. And if you can read any of this stuff, and it doesn't really matter whether you can or not, but, oh, and my laser pointer is getting pretty dim. It kind of says what you would expect. It talks about routines and subroutines and what they call preparatory routines, think linking loaders. So, that settles it, right? Von Neumann and Goldstein invented the API. Well, the ACM would beg to differ with you. In 1967, they awarded the second ever Turing Award to Morris V. Wilks for building a machine called the EDSAC, not the EDVAC. And what it says in the yellow print that you can't read there is, he is also known as the author, with Wheeler and Gill, of a volume, Preparation of Programs for Electronic Digital Computers, in 1951, in which program libraries were effectively introduced. So this raises a question. If Goldstein and von Neumann came up with the idea, why did Wilks get the Turing Award? The answer is basically that Goldstein and von Neumann were peddling vaporware, which isn't surprising given that there were no machines at the time, right? So what could they do? If you're writing a book about programming computers, well, it wasn't a book, it was a report, and there are no machines. Kind of the best you can do is guess. And here is a quote that I think describes it better than I could from Martin Campbell Kelly's, basically a historical reference to that period. He says, in Planning and Coding, which was the thing written by Goldstein and von Neumann, a program consisted of a main routine, a set of subroutines from the library. The routines were loaded in memory, starting at the low end. Because a subroutine might end up in any arbitrary location alpha, it would be coded relative to 0. Once in memory, it would have to be adjusted by adding alpha to each address. This adjustment was to be performed by a preparatory routine in the high end of memory. Goldstein and von Neumann's preparatory routine would have required extensive operator intervention, and it is difficult to imagine that it would ever have worked in practice. So there you have it. They had a good idea, but they did not know how to make it work. Wilks' machine, on the other hand, was the real deal. Here it is. It was, as I said, called EDSAC. It was built at the University of Cambridge at their mathematical library, and here are its vital statistics. It was the world's first stored program computer. It came to life on May 6, 1949, and it was immediately useful to all the other departments, astronomy, biology, and so forth. It ran at the blistering speed of 650 instructions per second. It had initially 512 17-bit words of memory, or you could use that as 256 35-bit words, because 35 is almost twice 17. I'm not making this up. It was stored in mercury delay lines. That was the technology of the day. And the reason they went from 512 then 1024 is because they could only get half of the mercury delay lines working initially. I/O was paper tape and teleprinter, and they both ran at about 6 characters per second. It used 3,000 vacuum tubes. It consumed 12,000 watts of power, and it occupied a full-size room. The best way to think about this is, it ran at 1/4 millionth the speed of a modern computer. It had 1/4 millionth the memory. It used 100 times the power, and it took up 1,000 times the space of a PC that you'd go out and buy today. The name EDSAC is in fact an homage to EDVAC, the one that Goldstein and von Neumann were working on. But that machine, EDVAC, didn't actually come into operation until 1951, 2 years later, and then only on a limited basis. It didn't do any useful work until 1956, at which time EDSAC had been working for 7 years, which raises an interesting question. Why did Wilks get it done so much faster? Given that he started later, why did he finish his machine so much earlier? And the answer is straightforward. He kept his machine simple. I have 2 quotes. The first from his biographer is, "The reason for the rapid completion, which was well ahead of any American computer, was that Wilks wanted to have a machine as practical computing instrument rather than a machine of the highest technological performance. To this end, he kept EDSAC simple, conservative in its electronics, and conventional in its architecture. Keep it simple." And then the second quote is interesting because it's modern. The second quote is from a guy named Andrew Herbert, who is currently leading a project at the UK National Museum of Computing to recreate the EDSAC, except for the mercury delay lines, which are like toxic. So they're using tin instead of mercury, I think. So importantly, the recently rediscovered drawings clearly show that the aim of EDSAC's designer, Sir Maurice Wilks, was to produce a working machine quickly rather than to create a more refined machine that would take longer to build. The refinements would come later, and many did, as the sequence of diagrams over the 5-year period shows. The first 2 EDSAC programs ever written were toys, and what you see on the screen, this is really cool, is the log and the output from the first program ever run on the first computer, first general purpose stored program computer ever to run. And what the log says is, 1949, May 6th, machine in operation for the first time, printed table of squares, 0 to 99. Time for program, 2 minutes and 35 seconds. 4 tanks of battery in operation. That means basically half of the memory was in use. And that scrap that you see is actually preserved in the museum in London. That is the first output from the first computer. The second program printed the first 170 primes starting at 5, and it was written by Wilks, and it ran, I guess, 4 days later. Then Wilks decided to write his first real program. So the first, I'm getting ahead of myself. I should describe the machine as it existed when these toy programs were written. It was a very simple architecture. The first 30 words in memory were the initial orders. Think bootloader. They were the program that read the program off the paper tape, put it into the main memory, and then executed them. And the bootloader, the initial orders, were stored on an electromechanical telephone switch. They were the only electromechanical hardware on this otherwise electronic machine. And technically what you had there was a JIT assembler, because the programs weren't written in binary code. They were written in assembly language on this tape, and the program running in the first 30 locations of memory read this stuff, turned it into binary code, stored it in memory, and executed it. Wilks and Wheeler decreed that users should never have to deal with binary code, because that's for machines only. And Wheeler, who was Wilks' graduate student, he wrote that 30-word initial order. Then Wilks decided to write the first real program. It solved this thing called the Aries integral, y double prime plus xy equals 0. And it turns out that this was useful in, I guess, some cosmology. Basically, it had something to do with ionization in the atmosphere. I don't know. But anyway, there's a wonderful quote. And keep in mind, as I read this quote to you, that this was the first programmer writing the first program on the first computer. By June 1949, I was trying to get working my first non-trivial program, which was for the numerical integration of Airy's differential equation. It was on one of my journeys between the EDSAC room and the punching equipment that, hesitating at the angles of the stairs, the realization came over me that a good part of the remainder of my life was going to be spent in finding the errors in my own programs. So this guy was way ahead of his time, right? There had only been a working computer for 2 months when he realized that this was the case. And he saw subroutines as a way out. He thought, if we had great subroutines, at least I could use those. And he gave the problem to his graduate student, who was David Wheeler. He was the same guy who wrote those initial orders. And Wheeler's architecture, which he finished in September 1949, that's pretty darn quick, given that he started in June 1949. He devised what he called coordinating orders and added those to the initial orders. Basically, the idea is you would annotate your program with little marks, like pi's and thetas and stuff, which would tell these preparatory orders how to relocate the subroutines in memory. Also, he came up with a clever linking convention that I'll show you on the next slide. And the computer ran the coordinating orders interpretively with no manual intervention. That was a big deal. The idea is that a single program was on a tape. It consisted of the main program and all of the subroutines, and the operator would put this into the computer, press the go button, which would cause the telephone switch to read these initial orders into the Mercury storage, and then it would execute them, and away it went. It would read the program off the tape, and the program would run. Wilkes, his advisor, who was not prone to overstatement, described Wheeler's work as a tour de force of ingenuity, and indeed it was. This slide shows you the actual calling convention. I don't have time to explain it, given how quickly I'm trying to do the talk. I'll tell you two things about it. One thing is it's self-modifying code, which may be a bad idea now, but was a great idea back then when your machine only had 512 bytes of memory, 512 words of memory, 1024 bytes. And the other thing about it is that it was reasonably powerful. You could have subroutines invoke other subroutines ad infinitum, though you could not have recursion. That would not come for another decade. But hey, that's better than BASIC, right, where you have go sub before return in line 472 or whatever. Here is an actual picture of the EDSAC subroutine library. It is contained in that file cabinet. That is the library. There are tapes of these subroutines, and the programmer, when he or she turns in the main program, would say, these are the subroutines I need, and she would take them out and punch them all up onto one tape. Basically, that's a tape duplicator in the middle, and that tape would be fed into the EDSAC. And for the less literal-minded, here's another picture of the subroutine library, and I'm just going to try to read the categories so you know roughly what it had. Floating point arithmetic, arithmetical operations on complex numbers, checking, basically think dynamic debugging. Amazing, no? Division, exponentials, general routines relating to functions, differential equations, special functions, power series, logarithms, miscellaneous, print and layout, quadrature, read, i.e. input, trig functions, counting operations, vectors, and matrices. And this thing was done basically a year after the machine. It's just staggering how much work they got done and how quickly. This is the book that introduced the world to subroutine libraries. It was the one that was referred to in Wilkes' Turing Award. It is the first text ever written on computer programming. And I actually had a prop. I was going to hold it up, but it's over there somewhere. Anyway, I have a copy over there that I can show you if you like. it was the definitive work on computer programming until high-level languages arose at the end of the decade. So basically, throughout the 50s, this was it. This was the book that described programming. It contained the entire library API, meticulously documented, down to how many instructions this takes, how long it takes. They had multiple versions of the same routine that were optimized either for space or time and told you when to use which. It's all in there. This book is specifically cited in Wilkes' Turing Award. It was published in 1951. It came from a tech report that they had completed in September 1950. They mailed it to every other place with a computer in the hopes that other people could take advantage of their work. And a guy from MIT saw it and said, this should be published. And that's how it came to be published by Addison Wesley. This is, I believe, their first computer book as well. And it's just the tech report with all of the English spellings translated into American. But otherwise, it's word for word the tech report. Wheeler took the key ideas from this book and presented them in a paper in 1952 at the ACM National Meeting in Pittsburgh, Pennsylvania, at the Mellon Institute. I think it was like the second ever ACM National Meeting. And the paper describes all of these concepts: the subroutine library, generality versus performance trade-offs when devising libraries, the importance and difficulty of properly documenting your library, the importance of information hiding, the interpretive routine, the idea being that the memory was so tight that basically you wrote your own little instruction set and you had interpretive code that read your little instructions that could be packed more densely than the machine's real instructions. Information, I already said that, or maybe I didn't, but yeah, the interpretive debugger, which was basically the machine emulating itself, so that you could, finding bugs on a machine with, no I/O facilities to speak of was damn near impossible. So they quickly came to the conclusion that they had to make the machine emulate itself one instruction at a time so that you could sort of single step it and print stuff out in between. Anyway, that's in there. And higher order functions are in there. Higher order functions in 1951. But yes, if you're going to be doing integration and differentiation and finding zeros of equations, you need higher order functions, and they had them. And they actually implemented all this stuff. Let me show you a few remarkable quotes from his paper. He says, "It should be pointed out that the preparation of a library of subroutines requires a considerable amount of work. This is much greater than the effort merely required to code the subroutine in its simplest possible form. It will usually be necessary to code it in the library standard form, and this may detract from its efficiency in time and space. It may be desirable to code it in such a manner that the operation is generalized to some extent. However, even after it has been coded and tested, there still remains the considerable task of writing a description so that people not acquainted with the interior coding can nevertheless use it easily. This last task may be the most difficult." 1952. All right, let me take you forward 42 years. David Parnas, who is a famous man in his own right, said this, and it was news to many. He said, "Reuse is something that is far easier to say than to do. Doing it requires both good design and very good documentation. Even when we see good design, which is still infrequently, we won't see the components reused without good documentation." Or how about this quote? This is the conclusion of Wheeler's paper. He says, "The prime objectives to be borne in mind when constructing subroutine libraries are simplicity of use, correctness of codes, and accuracy of description. All complexities should, if possible, be buried out of sight." Well, let's jump forward 52 years to my API design talk at UPSLA. And by the way, this was still news 52 years later. I said APIs should be easy to use and hard to misuse. It should be easy to do simple things, possible to do complex things, and impossible, or at least difficult, to do wrong things. So that's the same thing he said in his first sentence. Documentation matters. No matter how good an API, it won't get used without good documentation. Yeah, I stole that from Parnas, and Parnas, I think, came up with it independently of Wheeler. And finally, I said, minimize accessibility. When in doubt, make it private. This simplifies APIs and reduces coupling. So, right, all of those ideas were already present 54 years earlier. And one last trick that Wheeler played on us. His entire paper was 2 pages long. That's it. It's like a masterpiece of concision. And if you're interested, I brought like 15 copies with me. Just, find me after the talk and I'll give you a copy. I think now it's pretty clear who invented the subroutine library. The primary inventor was Wheeler, the graduate student. His advisor, Sir Maurice Wilkes, and Stanley Gill was a minor contributor. They are the three authors of the book that I showed you. So why didn't they discuss the API as distinct from the library? Well, because at the time, the two were isomorphic. There was only one machine architecture. Hell, there was only one machine. So you didn't really think about portability, right? You were writing a program for the machine and you had this library to help you do it. There were no legacy programs, so you didn't have to think about backward compatibility. So there was no reason to think about the API as a distinct object from the library. It just was the library. And clearly they did understand good API design principles. I hope I proved that to you with the last few slides. So when did people start considering the API as an independent object? Well, the field progressed and existing subroutine libraries were re-implemented. Why? Because new hardware was built. And once they had new hardware, they could simply port the existing APIs and keep using the original programs, thus preserving people's investment in code and in education. Also, new algorithms were devised, and if you want your subroutines to run faster, once again, you can write new implementations using the same APIs, and that gave life to APIs independent of the libraries. So when did people actually start using the term application program interface? It's very hard to find out. Here's my best guess, and this is my own personal research. I think this 1968 paper, which is on graphics, it's called Data Structures and Techniques for Remote Computer Graphics, is the first use of the phrase application program interface in a paper. I actually went so far as to contact the author of this paper, and he said, I don't know of any earlier uses, and in fact, I forgot that we used it. So there you have it. Merriam-Webster says the first use was 1974, and this paper beats that by 6 years. So until I hear anything older, this is the first paper that actually used the term application program interface. The paper first dances around the term. It says, normally, the interface between application programs and the system is desired via Fortran-type subroutine calls. The system has been designed to be essentially hardware independent in the sense that the implementation either in the central or satellite computers may be recoded for different or improved hardware while still maintaining the same interface with each other and with the application program. And then it runs with it. It says, finally, hardware independence at the central computer means that a consistent application program interface could be maintained if that computer were replaced. This also applies to the satellite processor if hardware independence can be achieved there also. Eventual replacement of at least a portion of the hardware is almost a certainty given the rapid rate of new development in computer technology. A sufficiently flexible hardware-independent system guarantees that technological advances will not make the system prematurely obsolete. That's great, right? They got it. They totally understood what the importance of APIs was. So what's going on? Well, you now live in an era where re-implementation is important because hardware is changing quickly, so the API has a life of its own, distinct from the library, and so it deserves its own name. I think many people understood this, and it's not a great intellectual achievement to come up with the notion of the API once the library has already been invented. In essence, libraries naturally give rise to APIs. APIs weren't invented so much as discovered. I think that if one person is to be given credit for the invention of the API, or one group, it's Wheeler and Wilkes. In inventing the subroutine library, they latently invented the API. So, now that we know who invented it, what exactly constitutes an API? It's actually a tricky question. I looked it up in various places. Merriam-Webster's did not have a very good definition. Here's what Wikipedia had to say as of the 16th of this month, or last month. In computer programming, an application programming interface, or API, specifies a software component in terms of its operations, their inputs and outputs, and underlying types. I think we should cross that out because types are only a part of it. There are a whole bunch of other things. You could say concurrency properties, types, preconditions, postconditions. So rather than trying to list everything, why don't we list nothing? Its main purpose is to define a set of functionalities that are independent of their respective implementation. Respective isn't doing anything, so cross that out. Allowing both definition and implementation to vary without compromising each other. This has the problem that various things on Wikipedia does, which is that someone was smoking crack while they wrote it. Yes, the implementation can vary, but the definition cannot vary. That's the essence of an API. So this is broken. Here's my attempt to sort of minimally fix their definition. I don't claim that my definition is perfect, but I think it's a decent working definition. An application programming interface, or API, specifies a component in terms of its operations, their inputs and outputs. Its main purpose is to define a set of functionalities that are independent of their implementation, allowing the implementation to vary without compromising the users of the component. Changes in blue. So there you have it. And this definition suggests a two-part test. If you can answer yes to both of these questions, you have an API on your hands. Number one, does it provide a set of operations defined by their inputs and outputs? And number two, does it admit reimplementation without compromising its users? If yes to both, it's an API. So now I'm going to take you on a whirlwind tour of 13 APIs that pass this definition, mainly just to sort of test the definition and see where it starts to break down. First of all, Fortran 2 in 1958 had a library with it. It was 28 math functions. It was defined in the manual in the lower right-hand corner of this slide. And this is the entire thing. You know, basically, my laser pointers, I'm out of juice. But anyway, that's it. Basically, you have in front of you the Fortran language API as of 1958. And if you were to write a Fortran program using that API, it would still compile and run today. It's pretty amazing, but they did get stability, you know, over half a century plus. What about the IBM 360 instruction set? Is that an API? It certainly passes the definition, but not everyone thinks of an instruction set as an API. So I leave it to you to tell me whether that's an API. Of course, the C standard library, just like the Fortran library, was an API. Because it was a newer language, it has a bigger API, but still not huge. It was written in 1975. And if you look at K&R from the C programming language book, which you all know and love, they absolutely understood the role of APIs in ensuring portability. I'm going to read you a quick quote from that. They said, input and output facilities are not part of the C language. Nonetheless, real programmers do interact with their environment. In this chapter, we describe the standard I/O library, a set of functions designed to provide a standard I/O programming interface, yet reflect only operations that can be provided on most modern operating systems. The routines are meant to be portable, in the sense that they will exist in compatible form on any system where C exists, and that programs which confine their system interactions to facilities provided by the standard library can be moved from one system to another, essentially without change. So what are they saying there? It looks to me like they're saying, write once, run everywhere, except that they couldn't come up with as snappy a slogan as Sun did, you know, whatever, 20 years later. What about the system calls in an operating system? In this case, the Unix system calls, 1975. This is the 6th edition manual. Operating system kernels have APIs, and they're called system calls. What about hardware? Let's take a look at a DEC VT100. There are all these escape sequences that you use to move the cursor around and replace text and print special characters and so forth. Does that constitute an API? It certainly passes my two-part test. And once again, I leave it to you to determine whether a peripheral control interface is an API. The BIOS in a PC is an API that allows the operating system, and in fact any program, to talk to the underlying hardware. What about a command line interface? Here's the MS-DOS command line interface from 1981. Once again, it passes the two-part definition, but it's not clear that it's an API. Another hardware one for you, the Hayes Modem AT command set. How many people know AT, DT, you know, blah, blah, blah? Guess what? That is still in very, very heavy use. Your cell phone uses that internally. Amazing. You know, it will not die. Anyway, is it an API? I think so, but up to you. What about, here's an interesting one. Take a look at this. That is the original Apple laser writer. So its API was described in this red book that says the PostScript language reference manual. So is it a language? Is it an API, or is it both? Well, I would claim there isn't actually a hard and fast boundary between languages and APIs, but if you made me say it, I would say this is an API that encapsulates a language, and I think that applies to a number of APIs. What about wire level protocols? You know SMB, the server message block protocol, which is what Windows, every version since 3.1.1 has used to share printers and files. Is it an API? I don't know, but it does pass the two-part test. Windows itself, there's another operating system API, you know, just like the Unix one, except several orders of magnitude larger. Java class libraries, those are just like the C API, except once again, several orders of magnitude larger. And now, of course, we have web APIs as well. So any, you know, heavily used web service has an API defined so that you can write programs against the web service. So that completes our whirlwind tour. Now let's have another look at our definition. The potential problem with it is that it may be too broad. It admits instruction set architectures, command line interfaces, wire level protocols, and the like. If this bothers you, if you think it's a problem, just add one more sentence. Say an API augments a programming language or a set of languages with an interoperable calling convention. Alternatively, an API may be described in an interface definition language. That last sentence is there to permit web APIs as APIs. So what can we learn from that tour? Well, first of all, APIs come in all shapes and sizes, and they just keep getting bigger over time. Many APIs live forever. They far outlive the original hardware for which they were written. APIs can create entire industries, both above them and beneath them. By above them, I mean that people write programs that call the API, and those programs and hardware that embodies those programs can create industries. And by beneath them, I mean reimplementations of those APIs. Simply put, APIs are the methods of operation by which components in a system use one another. They are the glue that connects our digital universe. Darn it. Let's try that again. So how does an API come to be? Very short section, 2 slides. I was going to make this part longer, but the talk's too long. This is just a quote from Stu Feldman, who wrote the Make tool. He says, the tool took off, and because it took off so fast, I never went back and fixed many of the design errors, because I didn't want to screw up my 15-person user community. So in this case, I would argue that an incompatible API change, it might have been in order, but that's water over the dam. So where do APIs come from? Well, as in the case of Make, software components are usually designed to address a specific pain point. Typically, when you've got pain, you're not the only one with that pain. And other people will use your component too, assuming it's good enough to ease the pain. And all of a sudden, its interface becomes a bona fide API, whether it is ready or, as in the case of Make, not. In other words, necessity is the mother of the API. So what makes an API successful? And when I say successful, I merely mean widely adopted. It's got to be the right thing at the right place at the right time, and it has to be good enough. Notice I didn't say it's got to be great. It just has to be good enough to solve the problem. By right thing, I mean it has to address a real problem. Technology for its own sake tends to lose. Right place, it has to be embedded in a successful language or platform, and the best language is seldom the most widely adopted. So don't write it in Haskell just because you think Haskell is cool. Right time, well, the market window can be very small. If someone else gets there sooner with something that's good enough, you lose. And by good enough, I mean it merely has to solve the problem. It doesn't have to be elegant or marvelous. For many details, see Dick Gabriel's marvelous essay, The Rise of Worse is Better. Darn it, I keep doing this. All right, so if you want your API to succeed, then that suggests that all you have to do is solve a real problem, do it on a successful language or platform, get it out quickly, and subject to those constraints, make it as good as possible. But success isn't all it's cracked up to be. If an API is successful and not good, it will cause real pain. I'm sure you can all think of examples of that. You know, buffer overruns, C libraries, there are thousands of examples. If, on the other hand, an API is good but not successful, it may influence a successful API in the future so that one can be good as well as successful. You know, every API designer has had APIs that never got anywhere. I certainly have, but I've still benefited from those APIs. So the moral of this section, you cannot know which of your APIs will take off or when. So design all of your interfaces as if they were going to be public APIs, because they just might be. Don't wait to design the quality afterwards, because you can't. You have to design it in from day one, and your API may take off while it still sucks, and then it will suck forever. The principles of good API design are now reasonably well known, and so are the costs of ignoring them. All right, now I'm going to take a brief legal digression, and this is the last section of the talk. Thank you all for your patience. So, first of all, we have always had the freedom to reimplement each other's APIs. For example, every single API in my tour has been reimplemented, many of them repeatedly. And each of the lines in this table has a story to tell. So for instance, if you look at that little line that says, you know, IBM PC BIOS, 1981, reimplemented by Phoenix in 1984, that reimplementation was what allowed the IBM PC compatible industry to flourish, and now basically every computer we use evolved from that architecture. So, you know, basically, API reimplementation has been fundamental to the creation of many, many industries, and this table pretty much proves it. Even the EDSAC instruction set architecture was reimplemented. Turns out that in Tokyo, they built a computer in 1959, a fully transistorized machine that used the same instruction set so they could take advantage of the libraries in that book that I showed you. And they did it without ever contacting Cambridge University once. Wilkes learned of it like a decade later, and he was thrilled that his APIs got this extended lease on life. API reimplementation is currently under attack. How many of you people knew this? Just by show of hands. Okay, just maybe you know, 15, 20% of you. Well, it is. In August of 2010, Oracle sued Google in federal court for reimplementing the Java APIs in Android. The suit alleged both patent and copyright infringement, and in May of 2012, the jury ruled there was no patent infringement, and the judge ruled that APIs weren't copyrightable. In February of 2013, Oracle appealed only the copyright ruling, and in May of 2014, the US Court of Appeals for the Federal Circuit reversed Judge Alsop, by the way, the same judge who asked me the question in the first place, reversed his ruling and said, yes, indeedy, APIs are copyrightable. And that is where it stands right now. In October, Google petitioned the US Supreme Court to hear the case, and just a few days ago, in this month, the Electronic Frontier Foundation and 77 computer scientists filed an amicus brief on the freedom to reimplement APIs. I also had it and was going to wave it around. Those 77 computer scientists, by the way, include 5 Turing Award winners, 3 National Medal of Technology, 1 National Medal of Freedom, the architects of many major languages, including like all the ones you saw up there before, and a bunch of others like Python and stuff. Anyway, that's where we are. And what does it mean for you if the Federal Circuit ruling stands? You cannot reimplement an API without permission from its authors. This may require you to pay big licensing fees or adhere to field of use restrictions. The people who made the API can just say arbitrarily, you can't use this API on a portable device, or you can't use this API on a pink device. Let me finish as quickly as I can. I know I'm running late. You know, less than 5 minutes, probably less than 3. It grants near perpetual monopoly on the API. Patents, they last for 20 years. Copyrights, life plus 70 years, or a flat 95 if it was a work for hire. That's forever for a computer, right? Basically, that means no one can ever use it but me, or under my terms. So do any of you guys use GNU, a PC, Samba, Wine, or Android? Don't answer that. I know the answer is yes. None of these things could have been built if their APIs creators could have asserted copyright and didn't want them built. And believe me, they didn't want them built. The right to reimplement APIs is crucial because new entrants cannot compete against an established player without reimplementing their API. It's the only way to do it. It's even good for the incumbent player Because if the incumbent player knows that other people can reimplement their APIs, they won't be lazy. They'll try and improve things. Otherwise, you know, think the Black Bell telephone of the 1960s. Also, software becomes more interoperable and less expensive if you can reimplement APIs. If you can't, you have to build your own API, and we have all these vertical silos that can't communicate with one another at all. Geeks get to spend more time hacking and less time talking to lawyers if they know that APIs can be reimplemented, and companies get to spend more time implementing stuff and less time suing each other or negotiating. A tiny bit of copyright law. It actually is important that you know this. The key tenet of US copyright law since 1879 is the idea-expression dichotomy, which is summarized in section 102 here. It says copyright protection subsists in original works of authorship. Works of authorship include the following categories: literary, musical, dance, graphic, blah, blah, blah. In no case does copyright protection for an original work of authorship extend to any idea, procedure, process, system, method of operation, concept, principle, or discovery, regardless of what form it is described in, blah, blah, blah. Darn it. Doesn't want me to finish my talk. So here's a short, so the important thing here is that it says method of operation. That's what an API is, right? It's a method of operation. It is how one software component operates another. And Judge Alsop agrees. He said each command line in an API calls into action a preassigned function. The overall name tree, of course, has creative elements, but it is also a precise command structure, a utilitarian and functional set of symbols, each to carry out a preassigned function. This command structure is a system or method of operation under Section 100B of the Copyright Act, and therefore cannot be copyrighted. Duplication of the command structure is necessary for interoperability. Yes, he got it. And one more quick quote from him. He says, so long as the specific code used to implement a method differs, anyone is free under the Copyright Act to write his or her own code to carry out exactly the same function or specification of the original methods used in the Java API. It does not matter that the declaration or method header lines are identical. So to paraphrase the judge, copyright protects implementation and not interface. Sadly, the Federal Circuit Court disagreed based on an obscure Third Circuit ruling concerning SSO, or structure, sequence, and operation, which is designed to protect against non-literal copying. I don't even know if the Federal Circuit understood what an API meant. You can read their decision and come to your own conclusions. Hopefully, the case is headed to the Supreme Court at this point. In conclusion, APIs date back to the dawn of the computer age. Wilkes and Wheeler invented them in 1949 or 1950. It just took us a while to realize they existed. In fact, took about 15 years. They are the glue that connects the digital universe. The magic of APIs is simply the fact that they can be reimplemented, and we have been free to do so since the time of EDSAC. I sincerely hope we don't lose this freedom in the next couple of years. Thank you for your patience. Right, and I don't have any time for questions, I think. Is that correct?
Thank you, Josh. Well, we have time for one or two questions, but only if they're short ones.
All right. And let me say that if you have more questions for me, just buttonhole me afterwards. I'll answer any questions you got.
Thank you very much. So thanks for the great talk. So I don't know if this is going to rise to the Roe v. Wade level, but it'll eventually come to the Supreme Court, I suppose, right? Because refactoring and the work that's involved in building an API over time, if somebody just gets to take the API and hand it off to somebody else and have them implement it, it gives you a massive time to market advantage, right? Because as a design itself, it's holistic. So, you know, all that work that went into figuring out what the right API design was over many years can be just taken up by somebody else and implemented on a different device and so on. So how do you account for that in this particular paradigm?
So two things. First thing you said was, this is probably going to get to the Supreme Court. And the answer is either it is or it isn't. You know, I sure as hell hope it does. That's where it is right now. That is basically Google, that was on my slide, maybe I forgot to read that line, but in October of this year, Google filed a plea for a writ of certiorari, which means, Dear Supreme Court, please hear this case. And in November, the EFF and 77 computer scientists, including, you know, I'm not going to list names, but Turing Award winners, you'd recognize them, and yes, I signed it too, said, Supreme Court, please hear this case. And in fact, there were like 4 other briefs written, or 5 other briefs by lots of other people you know, not just computer scientists, but famous lawyers like Pamela Samuelson and 50 other law professors. So yes, I hope it'll get to the Supreme Court. And the next thing you said was, isn't it terrible that, I'm paraphrasing you here, isn't it terrible that you spend ages writing a good API and other people can just up and re-implement it? So as someone who has spent 25 years of his career implementing APIs, no, it's just great. That's the way the world is supposed to work. If you can't, without it, we would not have Linux, or any of the other Unix-like operating systems. Yes, and my point is, first of all, if you look at the copyright law, it specifically says that sweat of the brow arguments do not hold. The mere fact that it was difficult to do something doesn't make it copyrightable. By the way, maybe patentable. There are other forms of IP protection. And if implementing an API involves practicing some patented technique, then maybe you can protect your IP that way. But that's another question for another day. Basically, I hope that I did a good enough job explaining sections 102A and B to convince you that you can copyright a work of art, but you cannot copyright an idea contained in that work of art. And I believe that the API definitely falls on the idea side of the idea expression dichotomy. One more question?
I have a very opinionated opinion how the Supreme Court should solve the issue. They should claim that the APIs are part of the federal commerce, and the Congress should be acting on it. So they will take it completely out of the copyright, they will go on the business side.
I only sort of got that. You said that.
So there is a federal law that says that the Congress has the power to do the Commerce Clause, right?
Yes.
And the Commerce Clause in the United States beats any other clause that we have, including the Copyright Clause. So at this point in time, blocking the APIs is going to put an impediment on the business. So from that point of view, I think they will avoid discussing the copyright issues. They will just go directly for the business aspect of the commerce and industry.
Well, that's an interesting opinion. I haven't heard it from the legal people who have written briefs on the case. And by the way, I encourage you, if you want to look at them, I put all 6 of them in my tweet stream. So if you want to read any brief in this Supreme Court, just look at, in this Supreme Court case, look at Josh Bloch tweet stream and you'll see them all there. All right, thanks a lot, and I apologize. I know I ran over.
Thank you very much.